Okay, hi. Thanks for the introduction. Hi, everyone. My name is Gai, and today I'm really happy to be here to discuss our work on optimizing code size for mobile applications directly within the linker. And this is a collaboration with my colleagues at ByteDance. So as you might have noticed, the apps in your phone keeps getting larger and larger. And this is mainly because app developers continue to develop new features to the apps, hoping to increase user engagement. And here's a chart showing the size increase of popular apps in iOS over time. In recent years, developers have been struggling to maintain their apps to be under the 200 megabytes download size limit enforced by the App Store. Sometimes they even have to cut their features in order to meet this target. On the other hand, however, users really love small apps. Here's a study showing that across different markets, reducing the app size by 10 megabytes each time will increase user conversion rate by more than 1.5%. So today, I'd like to talk about what we can do to reduce the code size from a compiler point of view. So let's start by first looking at some of the state-of-the-art approaches. On the high level, the recent efforts mainly focus on enabling size optimization globally. This is especially important because most of the redundancies in your code exist only across compilation units. And as a result, most recent efforts focus on utilizing link time optimization, or LTO, where passes such as the machine outliner is applied globally to maximize its effect. So here's an example that uses a monolithic LTO-based approach, where the LLVM compiler generates LLVM bytecode for each file in parallel. The link time optimization first merges all bytecodes into a single giant module, and then invoke the LLVM optimization path pipeline on this merged bytecode, all using a single thread. With this approach, the whole program is merged into a single compilation unit. Thus, the passes is naturally able to optimize globally. This approach turned out to be very effective in reducing the code size. However, it incurs a very significant build time overhead that is around 3 times slower than using the non-LTO baseline. To solve the compile time issue of monolithic LTO, ThinLTO was designed to support multi-threaded optimization while still enabling global optimization. Traditionally, ThinLTO mainly focused on improving performance, and this recent work mentioned here extended ThinLTO for size optimization. This is done by essentially running the codegen part twice. In the first round, they collect the potential outlining candidates across modules without actually committing to outline them. Then in the second round, they make the outlining decisions globally based on the results collected from the first round. This approach improves compile time, but since we still need to run the codegen twice, the build time overhead is still around 40%. Now, within our company, we do have some additional challenges for deploying our solutions. First, we would like to minimize the changes to our existing build pipeline so that we can easily integrate our optimizations. Secondly, we prefer not to increase build time too much. This is because our build machines currently enforce a hard timeout of 2 hours to streamline our release cycles. And any changes that significantly increase the build time would be unacceptable from our build team's point of view. The last point here is more specific to our own build flow. We have a multi-repo setup where a significant portion of code is pre-compiled into binaries, and the corresponding source code is not available during build time. In fact, we estimate that around half of our source code is only available in binary form during builds. And on a more general sense, many applications contain significant portions of third-party libraries where the source code or the IR is not often available. So it would be great if we can devise optimizations that are effective on binary objects as well. So now let's look at how the previous two approaches compare in these 3 aspects. First, the monolithic LTO-based approach is easy to integrate since it mostly involves adding compiler and linker flags. However, the build time overhead is significant as we discussed before. And since LTO optimizations require the IR to be available, we won't be able to optimize binary objects. And for the size-optimizing thin LTO approach, in its current form, it does require some changes to the build pipeline to be able to run the code gen twice. The build time, while significantly reduced, is still non-trivial due to its 2 code gen run setup. Lastly, like full LTO, it also needs the IR to be available, so it couldn't optimize binary files directly. Now our question is whether there's another approach that can potentially address these 3 challenges. Well, our proposal here is to build an optimizing linker, where the linker itself performs code size optimizations without the need to re-invoke the compiler's parse pipeline. So note that the existing linkers are already very good at symbol-level manipulations, such as that symbol stripping, function deduplications. However, there's currently no sophisticated code transformations inside functions, and that's what we will focus on. So would an optimizing linker help solve these 3 challenges that I mentioned before? Well, first, a customized linker would be easy to integrate by simply asking the client to use our customized version of the linker. Secondly, we can write lightweight and specialized passes in the linker so as to minimize the build time overhead. And lastly, since linkers can naturally optimize binary objects because they have full visibilities on them. Now, before we dive into the details, I'd like to compare our proposal with another well-studied approach called post-linking optimization. So here I'm showing a representative post-linking flow using tools such as Bolt. So the high-level idea is to reparse the executable binary after linking. Then we conduct optimizations on the binary and finally output the optimized version. So when comparing direct linker approach versus the post-linking optimization, we really do not see a clear winner. Rather, both have their pros and cons. So for linker optimization, we would need to implement one implementation for each linker that we support, while post-linking optimization is independent of specific linkers. On the other hand, linker optimizations are easier to integrate into the existing build pipeline by simply adding linker flags, while post-link optimization would require us to add and maintain another tool in our build flow. So we chose to implement our optimizations within linker in this work, mainly for easier integration into the build pipeline. So in the rest of the talk, I'm going to introduce an infrastructure for code size optimization in the linker. It's currently implemented on top of Apple's LD64 linker, and we are looking into porting it into LLD. So our techniques are generic, and it does not rely on specific linker features. So we don't anticipate any significant difficulties importing the passes across linkers. So currently we target the ARM64 architecture because it's the dominating architecture for recent mobile applications. So we will show that our techniques achieved more than 10% reduction in binary size, and the end and build time overhead is less than 10%. So our optimizations can be divided into 3 main parts. First, we design utilities and analysis to decode instructions, as well as to hash arbitrary sequences. So hashing is a common routine that we will use across optimizations. We then perform transformations to optimize code size. This includes an outlining pass and an identical code folding pass. Finally, we need to update various non-code sections to keep them in sync with what we just changed in the code. So let's go over a simple example here to understand our outlining pass. So on the right-hand side, I'm showing you a small function that we will use as an example. Note that this one will only be a sketch of the flow, and I'll skip some of the details. So first, we need to decode the bytes of the instructions so that the linker will understand. So we wrote our own decoding logic to extract useful information from the binary encodings of the instructions. So as we prepare for outlining, there are certain instructions that we should not touch. One example is the target of a branch instruction, because outlining them would likely introduce incorrect control logic. Another example is instructions that are endpoints in the range described by the exception handling table. We call these instructions pivot instructions, and we keep track of them throughout the flow. The next step is to collect sequences of instructions to outline. We call these sequences the outlining candidates. We adopt a simple linear scan-based algorithm where we hash every sequence of a certain length. So for example, here we look at every sequence of length 5, then hash each sequence based on its instructions and the relocations, and store the hashes into a table. We go through these sequences one by one while skipping any pivot instructions that we had identified earlier. So if two instruction sequences are identical, then they will have the same cache. Such repetitive sequences are potentially good candidates for outlining. Note that in practice, we only consider sequences up to a certain length. This max length is a configurable parameter in the compiler. So a larger max length considers more sequences, but consumes more time. Increasing the max length gives a diminishing return, and in practice, we found that a max length of 12 is enough to capture almost all the repeated sequences in the programs. So we chose to use this linear scan-based algorithm mainly because of three reasons. First, it's easy to implement and debug. Second, it has a linear time complexity if we set upper bound for the length of the sequences to consider. Lastly, the algorithm is also exhaustive since it considers all the potential sequences for a given length. Thus, we are able to uncover all the possible outlining opportunities. Now, after we examine all the sequences in our program, we sort the hashes by their probability, where the probability is determined by both the length of each sequence and their frequencies. After sorting them, we can then decide which sequences to outline based on how profitable they are. One choice can be to outline all the sequences that can reduce the code size. This will maximize the size saving. And in our path, we also have configurable parameters to control the aggressiveness of the candidate selection step. Now we are finally ready to make changes to the code. In this example, let's say we have just determined to outline all these color-coded sequences. So we modify the call side to insert the branch instruction to these newly created functions, whose contents are shown on the far right. Note that each of these small outline functions will be called many times in a program, and that's why we can save code size by sharing these common code sequences. In addition, since we changed the logic of the functions, we also need to update the destination addresses of control flow instructions within the same function. So for example, we will need to update this CBZ's relative offset to point to the correct destination. Finally, linker code often contains relocations that point to things like callee addresses or data section contents. Since our outline path is scheduled before relocation resolution, the relocation that our path sees are still in symbolic form. Thus, all we need to do is to preserve these symbolic relocations, which will then be resolved by the downstream relocation resolution step. So our final step is to update some non-code sections to make their content consistent with our changes. So one example is the debug info section. So here in this example, our outliner reduces the size of function 4 by 20 bytes, which moved the end PC value of the function to 20 bytes before its original value. So here I'm showing the debug information entry for this function, and we need to modify its high PC value as shown here. To achieve this, we wrote a customized debug info linker that is aware of our code changes and updates the information accordingly. So for similar reasons, we also need to update the debug line section for the line table, as well as the exception table section to correct the exception handling information. I'll skip the details here, but the process follows a similar spirit as the debug info section. So in addition to the outlining path, we also worked on another path called identical code folding. So outlining reduces redundancy at the instruction sequence level, while ICF here detects and removes functions that have identical instructions. So ICF is already a mature path in LLD, and here we enhanced the existing ICF path in LLD64. So specifically, we made the size optimization more aggressive. We improved the compilation time of the pass and made it safe under pointer comparisons by using redirections when jumping to identical functions. So I'm going to skip the details on this too, and I'm more than happy to chat about this offline. So we implemented these two optimization passes in C++ in LD64, which are inserted into the LD64 optimization pipeline as shown on the right. So for the experiment, we used 3 commercial iOS apps from our company, which includes a news recommendation app, a short video hosting and sharing app, and an enterprise collaboration client. So each app is written with a mixture of Objective-C, Swift, C++, and Rust. And each application contains around 1 million to 2 million functions. The apps are built on a build machine with a 6-core CPU and 64 gigabytes of RAM. So here's the size-saving results of our passes on the 3 apps. So across the apps, we observed around 12% to 13% binary size reduction overall. And the SAF safe pass reduced the code size by around 5%, and the rest is contributed by dot lining pass. And on the other hand, we did not observe any performance degradations from production data. We think this is mainly due to the UI-heavy nature of our mobile apps. So this means that the additional control flow overhead that we inserted is likely to be negligible when we compare them to the large number of system calls that we have in those UI-heavy applications. So in addition, also the reduced code size might actually help in terms of instruction cache performance. So finally, we also measured the overhead or the overall build time for release builds as shown in the table on the right. So in our build pipeline, the link time takes a little more than 10% of the overall build time. And our 2 passes takes about half of the overall link time. Across the entire build process, our additional optimizations increased the end-to-end build time by less than 10%. We also tried to enable monolithic LTO on our apps to compare its build time overhead with ours. And we observe here, on average, monolithic LTO increased the link time by over 2 hours for our applications. So in summary, we introduced a framework for native code size optimization within the linker. It requires minimal changes to the build pipeline and has more build time overhead. In addition, our framework can optimize binary libraries as well. So we do have a write-up on this with more details that is available on our archive here. So you are more than welcome to take a look, and I'm happy to chat about it offline. So finally, we are also actively hiring engineers to join our compiler teams here at ByteDance US. Please feel free to get in touch. And thanks.
Thanks, Guy, for the talk. We can take questions. I have a mic, it's moving. If you want to ask a question, you can also queue in those 2 mics, but yeah.
Thanks for the talk. That's great. I'm just curious, so the build time or the link time and the build process downsides of both LTOs make sense, but I'm curious if you have a size comparison, if you just ignore those downsides, like how did that compare relative to your passes?
Yeah, so we look at a few examples. So the first one here is the full LTO. And second one is the thin LTO, so for size optimization. So we are slightly worse than them in terms of the size gain. But in the meantime, we are still making incremental changes to the optimizations. So we are confident that we can reach their level soon.
Thanks for the talk. You mentioned one of the criteria for the decision compared to LTO's options was that, like, to be able to work with libraries. Do you have any data how it helped, like, to optimize libraries, and, like, do you share any code with the? Were you able to find common code between libraries and binaries, like your main binaries?
Yeah. So for us, like almost 50% of the code are for libraries, and then since the linker doesn't really distinguish between like function from the source or function from the binary. So it's more or less maybe I would say like 50% of redundancy actually from libraries. So it's relatively proportional to the number of functions from each of the sources. So I'm not sure if I understand, answer your question.
That
Yeah.
answers. And another, do you think it would be profitable to have special thing LTO bus that is heavily optimized on code size? Kind of basically the same, but in LTO implementation.
Yeah, that would definitely help. Like if the library itself built with full LTO for size, then it definitely helps. And also since the linker can dedupe like repetitive functions, then outlining them will also help from when we build the libraries.
Thank you.
Yeah, thanks.
First, great talk. Did you run into any problems in, say, stepping at the debugger assembly level to map the outline code back to the actual line of code, so to speak?
Yeah, that's really a key challenge for us. So we have to do all this work, including writing a debugging for linker in the Apple platform, where we basically have to record what we changed during outlining and modify the debugging for entries accordingly to fix them, basically. So does it make sense?
Well, I think more than just ending the high PC, you've also got to say...
Yeah.
you
The
have
line
to-
tables also, everything.
Right.
Yeah.
So I guess that covers the debug line info. Did you do any, changing topics slightly, did you do anything in regards to studying the performance of a compute-intensive program where the
Right.
jump to the code on another page could be where you could be page thrashing as a result of that, or how do you minimize?
Not in our case, but one of the references they apply full LTO, which is basically in effect very similar to us, and they did experiments on some Swift performance benchmarks, and then I think they don't see much changes in performance somehow. But that's a great question.
So you're saying that your performance is going to be very similar to what LTO gets us now, but faster.
Yeah, pretty much, yes.
Thank you.
Yeah, thanks.
Hey, one question I had was when you're trying to reconstruct the control flow by essentially disassembling a binary, do you have any issues particularly on ARM64 with indirect jumps? And I know this is an issue that Bolt has because I've read Bolt sources and found they have like a weak heuristic to try to figure out when
Right.
we have indirect jumps. Is this an issue you've encountered?
So I think most of the indirect jumps are still in the relocation form, so the symbolic form in the linkers. So really, we don't need to do much. So there are things like there are some code sections that are actually data. So for example, like the indirect jump table. Then those we just have to detect them and either fix them or we skip optimizing those functions.
Right.
Yeah.
Okay, so you bail out then if there's not
Yeah.
a jump table. Got it.
Yeah.
Okay. And then a similar vein in the previous question as well is you talked about the linear scan. So you do this hashing on every function,
Right.
and then you outline the code. How do you decide where you place the outline code? Because you have the potential there to introduce a page fault, right?
Right.
With
That's
that,
it.
like depending on how do you decide where the outline code goes?
Yeah, right now all the outline functions are next to each other, and we and like you said, page fault is a concern, but we haven't really studied the effect of it, but I think we can look into that.
Cool. I look forward to the LLD work.
Yeah, thanks.
So you mentioned improving ICF over what's been implemented in LLD64. Do you know how does your implementation of ICF compares to the one that's in LLD? Like, does LLD already have all those same features, or would it also
Pretty much.
benefit from those improvements?
Yeah, I think LD is pretty much pretty mature and then it's really great. So yeah, this is mainly just to improve LD64. So I don't see much more improvement we can do at the LLD side.
Okay, thank you.
Jun from Uber.
Yeah.
So how many times do you do the machine outlining
Just once.
Just one.
Yeah.
But you know, you can iterate it, do the machine learning to further reduce the binary size. The CDO
Yes.
paper is about 5 times. So
Yes,
in your slide, when you compare the size, how many times do you have for CDO paper?
So we only, so for the, you mean the final comparison?
You have a comparison between CDO paper and yours.
So yeah, I just took the numbers from the papers, basically the final. So this 70, sorry, this is a typo in the table. So the binary is actually 70.6%.
17 is 1 time or 5 times?
5 times for
5
binary.
times. Okay.
So
but yours is only 1 time.
yeah, that's right.
Okay. Or why don't you do?
Because
more
we
times?
don't observe much improvement if we run it many times. Maybe the code characteristics are different.
Fair enough.
So more questions can go offline. Thank you, Guy. It
Thanks.
was an amazing talk. Next talk will begin in 5 minutes.